Okay, everybody, here is the end of chapter 7. I'm actually going to have the periodic table here for you, that way you can kind of see it. Okay, so now we're going to talk about periodic trends. Specifically, we're going to talk about the changes. What is ionization energy and its changes? What do we mean by electron affinity and its changes? And also, what is the definition of atomic radii and the patterns on the periodic table? All right. So the ionization energy. The ionization energy is the energy required to remove an electron from the gaseous atom or ion. So if you're looking at the example given to you on this slide, you have some element, an electron is removed to make it a cation. So it's the energy required to remove an electron. The first ionization energy is the energy required to remove the highest energy electron of an atom. The value of this is smaller than that of the second ionization energy. I'm going to go through the slide first, and then I'm going to kind of go through it step by step. As you go across a period from left to right, the initial or the first ionization energy increases. Electrons added in the same principal quantum level do not completely shield the increasing nuclear charge caused by the added protons. Electrons in the same principal quantum level are more strongly bound as we move from left to right on the periodic table. Okay. So here's our periodic table. What do we know about the elements on the periodic table in regards to, say, valence electrons and wanting and gaining electrons? We know that the alkali earth metals, and the metals in general like to give electrons away. We know that the nonmetals, especially the halogens, want to gain electrons. They don't want to give any electrons away. They want to gain electrons. Therefore, for the ionization energy, okay, the energy it takes to remove an electron increases as you go from the metals to the nonmetals. So your IE increases as you go from the metals to the nonmetals. And this is because the electrons in the same principal quantum level, which is the same rho, the same energy level, are more strongly bound as we move from left to right on the periodic table. Okay, so the electrons added in the same principal quantum level, so all electrons that are added within energy level 3, for example, do not completely shield the increasing nuclear charge caused by the added protons. We're going to talk about effective nuclear charge when we get to atomic radii. As we go down a group, the first ionization energy decreases. Why? Because as you go down the periodic table, we're adding the energy levels. So there's only one energy level for hydrogen, but by the time we get to francium, we have 7 energy levels. These are all shielded, and these guys have a lot of electrons, especially ones on the outside. They're farther from the nucleus. So as N increases, the energy level, number of energy levels, the size of the orbital increases, and the removal of electrons becomes easier. Okay, it's kind of like if you have lots of cats. Okay, if you have 1 or 2 cats, you should keep an eye on them. It's easier to keep an eye on them. You know, it's going to be harder to remove those cats from you. However, if you have hundreds of cats, 1 cat disappears or someone comes to take the cat from you, not really going to notice. I know, very loose example, but hopefully it gives you the idea of what I'm trying to get at with the electrons. Okay. So the first ionization energy for phosphorus is 1,060 kilojoules per mole, and that for sulfur is 1,005 kilojoules per mole. Why? Well, let's find where phosphorus and sulfur are on the periodic table. Here's phosphorus, here's sulfur. Phosphorus has 5 valence electrons, sulfur has 6. Which one is going to require more energy to remove the electron? So if we look, it's going to be phosphorus. Why? Well, the first thing is we know the trend is that the ionization energy is going to increase as we go towards the halogens. But if we're looking at the numbers, phosphorus is actually higher than sulfur. So because they're neighboring elements, they have the following valence electron configurations. Ordinarily, the first ionization energy increases as we go across a period. So that's what we would expect, right? Right. However, in this case, the 4th p electron in sulfur must be placed in an already occupied orbital. So the electron-electron repulsions that result cause this electron to be more easily removed than might be expected. The energy change associated with the addition of an electron to the gaseous atom. Oh, sorry, we're on to electron affinity. Whew. Okay. So where ionization energy is the removal of an electron, electron affinity is gaining an electron. Okay. So as we go across a period from left to right, electron affinities become more negative. The more negative the energy, the greater the quantity of energy released. So the electron affinity of an atom, how badly does the atom want that electron, depends on the atomic number. Changes in electron repulsions can be considered as a function of electron configurations. Again, if you have an electron configuration where you have 3 electrons kind of all evenly distributed, but then you have the one that wants to or has to share, or like that, that's going to change the affinity or the ionization energy. So electron affinity becomes more positive as we go down a group. Electrons are added at increasing distances from the nucleus, and the changes are relatively small. Finally, we have the atomic radii. Okay. When we refer to the atomic radius, we are referring to the radius when it's bonded to another atom. Non-bonding radius, we refer to the van der Waals radius. That's different. So when we're talking about the atomic radii, we're talking about the bonding radius or covalent bonding radius. The atomic radii trend is determined by the number of valence electrons, and most importantly, what's called the effective nuclear charge. The effective nuclear charge is the inward pull of the nucleus on the electrons. Because what charges the nucleus? Positive. Electrons are negative. So you have to realize that those electrons that are shielded by the outermost levels actually have them more influenced or are influenced more by the nucleus itself with the positive charge. So this is reflected by the shielding, this whole effective nuclear charge, the pull of the nucleus. The inner electrons are shielded by the outer electrons, meaning that they are actually held on tighter by that nucleus. So the outer electrons, the valence electrons, are not as shielded. Okay. Go back. Okay. So the atomic radius decreases in going across a period from left to right. I'll let you go see that, so that way you could copy those notes down too. So why does the atomic radius decrease from going from left to right? This is because of an increasing effective nuclear charge. The valence electrons are closer to the nucleus, which decreases the size of the atom, because the closer you get to that octet, the closer you are to completing that energy level, and the closer it's going to be to the nucleus grabbing a hold of it or kind of drawing it in. Okay, and that's what we mean by the effective nuclear charge. So the atomic radii decreases as you gain electrons, but then as you add energy levels, the atomic radii actually increases because you're adding energy levels. Okay, so if we look at this chart, this demonstrates what happens to the radius of an atom as you move down the periodic table and as you move across. Okay. So let's predict the trend in radius for the following ions: the beryllium ion, the magnesium ion, the calcium ion, and the strontium ion. So all of these ions are formed by removing 2 electrons from an atom of group 2A element. In going from beryllium to strontium, we are going down the group so the sizes increase. Beryllium, strontium, magnesium, calcium. Therefore, beryllium has the smallest radius and strontium has the largest. That really does sum up the trends in the periodic table. Let's just go over some example problems while we're staring at this periodic table before we move on just to the groups of the periodic table. Okay, here we go. Oh, another trend. Sorry, real quick. It's called metallic character. Here, hold on, let me. Okay, metallic character is obviously going to increase. Metallic character is also going to decrease as you move towards the nonmetals. And as we move down the periodic table, the metallic character increases as well. Okay. Let's see. So, ruh-roh. Okay, guys. So for the ionization energy, let's do some example problems. And again, just to review, ionization energy is the energy required to remove an electron. It generally increases as you move from left to right and decreases as you move down. You do have a first ionization energy, which is generally the most energy to remove, the least energy to remove an electron. The second and third ionization energies refer to the fact that if it's not that you're removing 2 simultaneously, it's removing the next electron and then the next one. And subsequently, each energy to remove an electron is going to become higher. So let's look at these examples and see if we can predict whose ionization energy would be higher. So if we have oxygen or chlorine, so if you look and see where oxygen and chlorine are on the periodic table, it's almost impossible to tell because you trace the path. If you go to the right, the ionization energy is going to increase, and then you go down the column and the ionization energy is going to decrease. So this is an example, not a very good one to start with, that tends to where you can see that the effects are going to counter each other and it's not obvious which one is going to dominate. So this one is a tie or an equal. All right, next we have aluminum or sulfur. So if you look and see on the periodic table between aluminum and sulfur, sulfur has a higher ionization energy because you're going to move to the right within the same row, and the ionization energy increases as you go to the right. So we have sulfur. Look for arsenic or antimony. Arsenic is above antimony. We know that the ionization energy decreases as you move down the periodic table. Therefore, arsenic requires a higher ionization energy. Finally, we have nickel or silicon. Nickel is going to have, nitrogen. Nitrogen is going to have a higher ionization energy because it is above silicon and it is also more to the right. So therefore, we're going to be looking at nitrogen with the higher ionization energy. Okay, moving on. Let's do metallic character and atomic radii. Okay, which one has more metallic character? Tin or tellurium? Well, if you look, tin is closer to the metals, so therefore tin has more metallic character. Phosphorus or antimony? Antimony, because as we move down the periodic table, it increases in metallic character. Germanium or indium? So indium is more metallic because you are also moving down the column and you're also moving left. Both of those leads to an increase in metallic character. But if you look at sulfur or bromine, based on trends alone, we really can't tell because it's kind of like the example that we just did for ionization energy. The effects tend to counter each other, so we really can't tell which is going to predominate. All right. Last one, let's talk about atomic size. Atomic radii. Okay. I want to just make sure I cover this. If you are an anion, typically the radius for an ion is larger because anions are larger than the parent atom from which they came. Likewise, cations are smaller because they're losing electrons. However, for the bromine ion or potassium, because the isoelectronic nature is the same, meaning you have the same number of electrons, you have to look at the nucleus then to look and see what's going on with the effective nuclear charge. And since bromine has one fewer proton, it has less pull on the electrons to tighten them in. So therefore, bromine is going to have the larger atomic radius. Finally, atomic size, carbon or fluorine. So, carbon atoms are larger than fluorine atoms because as you go between carbon and fluorine on periodic table, you're going to move to the right within the same period. As you move to the right, the effective nuclear charge experienced by the outermost electrons increases, resulting in a smaller radius. Because remember, that effective nuclear charge pulls those electrons into the positively charged nucleus. Next, we have germanium or carbon. Germanium atoms are larger because you're moving down the periodic table, and therefore it adds more energy levels. All right, let's look for aluminum or nitrogen. If you look, aluminum is further down on the periodic table. It's also further to the left. Both of those indications that it's going to have a larger atomic radii. And then aluminum and germanium, the effects are going to counter each other. So we really can't tell which one's going to predominate. Last summary. I just want to make sure you understand the difference, what electron affinity is. Electron affinity isn't like the trend for ionization energy, the atomic radii, or metallic character. Electron affinity refers to the energy when electrons are gained. So that when we're looking at the values or comparing elements, we're really talking to if the electron affinity becomes less exothermic or more exothermic, meaning that it's going to become more positive or more negative as you gain electrons. So group 1A metals, as you move down the periodic table, the electron affinity becomes more positive and less exothermic. So it actually gains less energy. However, from moving left to right, it becomes more negative and more exothermic. That's that. Okay, now let's talk about the elements of the periodic table. Okay. So we've talked a lot about the periodic table and the trends. We've talked about valence electrons, the oxidation states, quantum numbers, electron configurations. We really haven't talked about the organization of the periodic table, though. So the first group in the periodic table, group 1A, are known as the alkali metals. Oh, well, your PowerPoint is going into the division. So we know that the majority of the elements on the periodic table are metals, and there is a line that divides the metals and the nonmetals, as shown by that line that I just drew. So everything to the left of that line are metals, everything to the right are nonmetals, and the elements on that line, except for aluminum, I think it's also antimony, but I have to check, are called metalloids because they exhibit semi-metal properties. Metals have low ionization energy and nonmetals have large ionization energies. Nonmetals also have negative electron affinities. Remember what that meant? That meant that they have more negative, or they become more negative or more exothermic as they gain electrons. The metalloids are the semi-metals, and they exhibit both metallic and non-metallic properties. So group 1A are known as the alkaline metals. Group 2 is known as the alkaline earth. These are our transition metals. Group 7A are known as the halogens, and these guys over at the end are known as the noble gases. Everybody wants to be like the noble gases. Down here are our rare earth metals. We have our lanthanides and our actinides. And this slide just shows you the division between the metals and the nonmetals. Make sure you know that hydrogen is a nonmetal. Okay. The alkaline metals are lithium, sodium, potassium, rubidium, cesium, and francium. They are the most chemically reactive of the metals. They react with nonmetals to form ionic solids. Hydrogen exhibits nonmetallic character due to its small size. Going down the group of the alkaline metals, the first ionization energy decreases, the atomic radius decreases, the density increases, and the melting and boiling points smoothly decrease in group 1A. Group 1A elements are highly reactive. Their relative reducing abilities are predicted from the first ionization energy by reducing, we're going back to redox. The energy change for a reaction and the rate at which it occurs are not necessarily related. Is that it? Oh my. Okay. And that's it. Okay, guys. That's it for now. I'll be back with chapter 8.